This is our second lecture in the discussion of magnetic fields, and now we're going to discuss the effect of electric currents and magnetism and the relation between the two. So as we discussed before, you can take a look at any magnetic system and look at the shape of the field. And here we have our typical north-south magnet and the field that's set up between those two poles. Now, if we take any normal piece of iron, as we said, the magnetic domains in any particular material tend to be randomly oriented. That results in a system which is neutral in a magnetic sense. Now, if we take a piece of iron which magnetizes easily and put it into the presence of a magnet, so here's the north pole of a magnet. The magnetic field will come out and curl round to the south. As you can see, what actually occurs is the particles will align, and this will result in the magnetization of the iron. So, in the presence of this magnet, this piece of iron becomes increasingly magnetized. In some cases, the magnetic domains, the spin and the angular momentum of the individual atoms in these different regions of the iron can become permanently magnetized. Buy a cheap screwdriver, throw it on the floor a few times. Eventually, you end up magnetizing it. So, in a piece of iron, the magnetic domains are random. Place it in a magnetic field, and then you'll end up with more parallel spins to your angular momentum in your atoms, and you'll have a magnet. We've also discussed current and magnetism. Now, if we switch on a current, we will end up with a magnetic field set up around our wire that will then influence any local magnetic system, such as a compass placed in the vicinity of that current. And that can be given by the right-hand rule. The direction of the current is the direction you place your thumb, using your right hand. If you're left-handed, I do apologize, but you have to do this with your right. So use your right hand, put your thumb upwards. Look at where your fingers now curl. Unless you're severely double jointed, they should be curling in a essentially counterclockwise direction. Now, if you reverse the current, your electrons are traveling downwards and your fingers are pointing the other way, and the magnetic field is curling in the opposite direction. That's the right-hand rule for finding the magnetic field from moving currents. We've discussed this previously, and this was just a bit of a recap, that when we have a moving current, we end up with a magnetic field. And we've been using a unit for current for quite a while here, referred to as the amp, named after Ampere. Here's Ampere. He was around during the French Revolution, good physicist, decent mathematician, spent a lot of time revolutionizing science, especially our discussion of electricity, and then eventually became a judge during the French Revolution and killed a lot of aristocrats. Now, Ampere came up with his own law, and Ampere's law relates the current through any surface to the magnetic field that's generated. And he was looking at wires and basically passing currents through different wires and looking at how those wires would actually influence one another. And his experiments came to define the permeability of free space, one of our constants that we've discussed previously. And the permeability of free space, which relates to magnetic fields, is mu0. And this is 4 pi times 10 to the negative 7 Tesla meter per amp. And this is a fundamental constant when we discuss magnetic fields. And this is Ampere's law itself. He was looking at the magnetic field generated by these currents and saying, if our current runs through this wire here, we will end up with a closed loop of magnetic field running this way. Try your right-hand rule here. Current's going up, so your thumb is upwards. That means the magnetic field is curling in a counterclockwise direction. the magnitude of that magnetic field at some distance r from the wire will be mu zero, this permeability that we just found previously, 4 pi times 10 to the minus 7, times the current. It's a magnetic field, of course, so the units will come out in Tesla. And there's what we're talking about, where we have our magnetic field here set up by the moving current through the wire, giving us a magnetic field of B being mu 0 I over 2 pi r, where mu 0 is 4 pi times 10 to the minus 7 Tesla meter per amp. So let's take a look at an example of using Ampere's law and calculating B for a wire. So let's find the magnetic field 2 meters from a long straight wire carrying a current of 10 amps. And as you can see, the length of the wire doesn't factor in here because what we're really dealing with is a thin cross section of the wire and the distance we are from the wire in radius. So, using Ampere's law, B here will be mu 0 I over 2 pi r. Our R is M and our I is 10 amps. Substitute in, we will end up with 1 times 10 to the minus 6 Tesla. Now this is a 10 amp current. This is fairly high. And remember, Tesla is a very big unit. So 10 to the minus 6th or millionth of a Tesla, about 2% of the Earth's magnetic field value, is a relatively weak field. So where do we usually apply Ampere's law? We can find B, but of course we can find other values, such as I, if we're given B. So here we have a 52 microcoulomb charged particle, and this particle is moving parallel to the wire. So this is a proton or electron or some particle that's charged, and it's just off to the side of the wire, and it's moving parallel to it. And remember one simple thing here, that a particle will not actually be influenced by the magnetic field unless it is moving. So a charged particle has to be moving to be influenced by a magnetic field. So we've got 52 times 10 to the minus 6 coulombs moving at 720 meters per second parallel to the wire. The separation of the particle and the wire is 13 centimeters, and the force turns out to be 1.4 times 10 to the minus 7 newtons. What we want to find is the magnitude of the B field, the magnetic field, at the particle's location. And what is I in the wire? So, if we want to find the magnitude of the magnetic field at the particle's location, stop and think about this for a second. We cannot do this simply using Ampere's law, but we have discussed previously the force due to the magnetic field. So the force is QVB, meaning our magnetic field will be F over Q times V. Substituting in, our force is 1.4 times 10 to the minus 7, our Q is 5.2 times 10 to the minus 5, and the velocity was 720 meters per second, giving us a small 3.7 times 10 to the negative 6 Tesla, a reasonable value. The current in the wire now, after we've found F, well, found I through, we found this through F, we found B through F, is mu 0 I over 2 pi r, so I will be 2 pi rb over mu 0. Substitute our values in, this will give us 2.4 amps. So don't forget the definitions that we've used prior. In conjunction with Ampere's law, we can find B, we can find F, we can find V. Where is this useful? Well, things like a current balance. With Ampere's law, if we take two wires and we separate them and look at the force between them or the current induced in either one, then we can actually say essentially how far apart they are. The deflection there, how close those two come to one another, really tells us how heavy something is. So we can make very, very accurate balances using Ampere's law and laser beams. So there is an application here. We didn't really define what the amp was before. We've just been using it. The amp is actually a constant current. If we maintain a constant current and we have two straight parallel conductors, essentially a very great length, infinite length, a negligible cross-sectional area, 1 meter apart, they'll produce a force of 2 times 10 to the minus 7 newtons per unit length between them. And that is how Ampere came up with his permeability of free space in newtons per amp squared. This won't necessarily be on an exam, but just in case you were wondering, that's how the amp was defined. And Ampere was looking at the magnetic field from two parallel wires. And here we have two wires with parallel currents. That's I1 and I2 going in the same direction. Now, if we reverse the direction of one of these currents, they would be referred to as anti-parallel, opposite direction to one another. But remember, each of these currents will generate a magnetic field, and that magnetic field will influence the other wire, as we just saw in the current balance. So looking at the magnetic field from two parallel wires is often a field of interest, and this is what Ampere was doing. So here, if we look at I2, we have a current running this way that will generate a magnetic field which will be circular in this sense. That magnetic field will then interact with the current of I1. So usually those currents can be fairly close together, and you can look at the force in these wires. And two parallel currents, as I said, if you reverse the current, the force will be reversed. Two anti-parallel currents will repel one another. Two parallel currents, both going the same direction, will have an attractive force. So this is a little different to two norths repelling, two souths repelling, or pluses and negatives attracting, and pluses repelling, negatives and negatives repelling. Here, if the currents are going in the same direction, they will attract one another. If one of the currents is reversed, the force between the magnetic force between them will be reversed, and the two wires will repel. So anti-parallel currents will repel, and parallel currents will attract. And that's where F equals BIL came from. This is what Ampere was working on. So the magnetic field due to two wires. If here we have two wires carrying currents of 5 amps in opposite directions, and they're separated by 10 centimeters, we want to find the direction and magnitude of the net magnetic field. So that's the total magnetic field of the system. First of all, at a point midway between the two wires. So halfway between the wires. If we look at this, one current is going upwards, one current is going downwards, both of 5 amps. This is an anti-parallel situation. So that means, with respect to one another, B net, the net magnetic field, is going negative. Both of these magnetic fields are going into the page. Do the right hand rule here. If you put your thumb along the right hand side magnetic current, and you can see the magnetic fields going in. If you put your thumb upwards on the left hand side, you'll see that the currents for the magnetic field is going the opposite way, but that means between the two wires the magnetic field is going in. They're both into the page, or the screen in this case. So both of them take a negative value because they're going into the screen. Substitute in. That'll be minus, add our two together, mu 0 I over 2 pi r, mu 0 I2 over 2 pi r. Essentially, this will end up with mu 0 over 2 pi r at the same point, I1 plus I2. This essentially here, we are looking at r over 2 for our radius because we're looking at 5 centimeters from each wire. So r here is 5 times 10 to the minus 2. So 2 pi, 5 times 10 to the minus 2, that's our distance of interest here between the two wires, right here, times 10 amps, because this is I1 plus I2, 5 amps plus 5 amps. That'll give us 4 times 10 to the minus 5 Tesla. Leaving this as negative is just fine. You could alternatively say this is 40 microtesla, or 4 times 10 to the minus 5 Tesla going into the page. Now, let's take a look at a point 10 centimeters right of the right-hand side wire. So here's the right-hand side wire. Let's look 10 centimeters to its right at a point P1. Here, the net magnetic field is going to change. Do your right-hand rule. Put your thumb this way and look at which way your fingers curl. That means that the field is coming out due to current 1, due to this current, and it's going in due to this current. So the field at this point is in opposite directions from these two. This is going in, this one's coming out in terms of the B field. That means we now have mu0 over 2 pi times I1 over R1 minus I2 over R2. That'll give us 4 pi times 10 to the minus 7, our constant, remember, over 2 pi. This is 5 amps over 0.1, so 5 amps over 10 centimeters. Now this distance is 20 centimeters, or 0.2 meters. So this will be 5 over 0.1 minus 5 over 0.2, which will give us 5 times 10 to the minus 6 Tesla. This is a positive value. Don't take that for granted, and you can even put the plus on here if you want to remind yourself. And this is out of the page, or out of the screen. So this is what's really going on between our current carrying wires. Not only will we have a magnetic field produced by these two current carrying wires, by the currents in these wires, but we'll also have a corresponding force on that magnetic field. So here we have our current I2, and here we have our current I1. Now I want you to look carefully at this diagram and do the right hand rule. If you put your hand here and you put your thumb in the direction of I1, that means your fingers will curl as if they're coming into the screen and then coming out. So they should be going in below the wire, and the field should be coming out above the wire. Okay. So the magnetic field here that's produced by I1 is going into the page here. So this magnetic field relates to this wire. This magnetic field that's coming out of the page, or out of the screen, relates to this current, I2. So this field goes with this current, this field goes with this current. That means these two wires are then influencing one another. So the parallel currents here will result in F2 being negative F1 and F1 being here. So these will be an attractive situation. These two magnetic fields are opposite, so these two wires will attract. Now, let's reverse the direction of I2. So now I2 is going this way. That means, doing your right-hand rule again, that the magnetic field from I1 is still going into the screen. The magnetic field of I2 over here by this wire with I1 in it is also now going into the screen. This means that both of the magnetic fields are in the same direction now, and they will result in a repulsive force. In other words, F is equal to I2BL. It's going to be I2L, and then you can simplify this through in terms of mu0 I1 for 2 pi d. This will be the force between the wires. So let's take two wires and put them close together and look at the B field effect on one another. So here we've got two wires, wire 1, wire 2, with current 1 and current 2 flowing through them. For wire 2, It's a distance d from wire 1. So here's the magnetic field going around in a circle due to this wire, and it's a distance d. Okay. So for wire 2, distance d from wire 1, what's the effect of one wire's magnetic field on the other? So B times 2 pi r is mu 0 I, of course. This is from Ampere's law. So our magnetic field is mu 0 I over 2 pi r. The reason it's 2 pi r is because this is a circular field that's generated by each of these wires. So for wire 2, a distance d from wire 1 is just mu 0 I2 over 2 pi d. Now the force on wire 1 from B2 is where we have to refer to another formula. So F1 now is equal to BIL, or B2 times I1L. And that essentially is B2 times I1 times the distance S here. Now, if we say this, as we did in the previous case, F1 now is mu 0 I2 over 2 pi d times I1S. This will result in this particular formula. Mu 0 I1 I2S over 2 pi d, where S is the length of the wire. That will also turn into force per unit length, where S is the length of our wire. Here's S, here's D. So F over S becomes mu 0 I1 I2 over 2 pi times the separation of the wires. So the magnetic force on a current carrying wire is going to be F equals BIL sine theta. And we've already talked about this, and we'll talk about this more in terms of particles in a magnetic field. Where we're going to go next is discussing things like solenoids and looking at twisting up our loops of wire and seeing what effect that has on our magnetic field. If we look at a loop of current though, now we're looking at something that's looped around and joined. So take our wire and put it in a circle and then pass a current through it. What will happen to the magnetic field? The magnetic field now is going to be looped around symmetrically with this wire. And that means the magnetic field due to a loop of wire is no longer 2 pi, but is now mu 0 over 4 pi. So I2 pi r over r squared, and this will reduce to mu 0 I over 2r. So for a loop of wire, we essentially eliminate our pi factor. And this is where we're going next.